This is part 2 of the two-part lesson on entropy. So for entropy values, you're going to go to your textbook, Appendix 4 on page A19. And we've used that appendix before. That's where we have our delta H zero of formation values. There's also a column for delta G zero formation. We'll learn about that later. And then there is a column for S0. So we have S0. That zero, remember, that means that standard state applies, which you may or may not recall is 1 atmosphere for gases and 1 molar if we have a solution. All right, so our units that they give us are joules per mole times Kelvin, which we could also write as joules, moles to the -1, Kelvin to the -1. All right, oh, they actually have Kelvin mole, but it doesn't matter if you write Kelvin mole or mole Kelvin. Okay, so we have our same type of equation for figuring out the delta S. So the delta S for a process, and that can be a chemical process or a physical process, is equal to the summation, the number of moles times the entropies of our products minus the summation times the number of moles times the entropy of the reactants. Okay, so let's do an example of that. So let's look at our Bunsen burner reaction. So we have CH4 gas plus 2O2 gas yields CO2 gas plus H2O. And that could be liquid or gas. We'll say liquid for this reaction. When you have this reaction happen, you get water vapor in the gas phase, but if you collected that water vapor and cooled it down, then it would condense into a liquid. But when we're doing these types of calculations, we have to be very cognizant of the states of matter. All right, so we want to calculate the delta S for this reaction. And before we do that, we're just going to predict the sign of delta S, what we think it's going to be. So we have a mole of gas, 2 moles of gas. We have 3 moles of gas on the reactant side. And we have 1 mole of gas. Oh, I need a 2 here. And 2 moles of a liquid. So we have gas going to a liquid that is becoming more ordered or less disordered. So we would predict a negative delta S. And now let's calculate that and see if we in fact do get that. All right, so our delta S then equals number of moles for carbon dioxide is 1 mole times, we look in our chart for the entropy value in that appendix, and we see that it is 214 joules per Kelvin mole. And then our moles cancel out. I'm not going to put in the units for the rest of it because it all cancels out to joules per Kelvin. All right, so that's for the carbon dioxide, plus, then we have 2 moles of water, 2. Then we look up the value of H2O liquid in the table, which is different from if we have a gas. And for that, we have 70 minus, now we do our reactants. So 1 mole times the value of methane gas, which is 186, plus 2 times the value of oxygen gas, which is 205. So when we do that calculation, we come up with a value of negative 242 joules per Kelvin. The moles all canceled out. So it did match our prediction of having a negative sign for the change in the entropy. So that means our system is more ordered after the reaction than it was before the reaction. And the same thing also works for a physical process. If we look at H2O liquid going to H2O gas, so the vaporization of water. So to predict the sign, we're going from a liquid to a gas. The gas is the most disordered. Gases have the most entropy, so we would predict a positive delta S for that process. We can calculate it now. So our delta S is equal to the entropy of the H2O gas minus the entropy of the H2O liquid. So that is 189 minus 70, and so we get a value of positive 119 joules per Kelvin, and it matches our prediction. That's it.